Bismillahirrahmanirrahim. Here we are going to deal with the second part of atom economy, and we are going to resolve and study some issues under the tool of atom economy. Now let's see. Now, before going to deal with the problems and the issues with reference to atom economy, it is more important to revise some important facts about the atom economy. So let's see. Like most other peoples, chemists are concerned with environmental pollution. This concern has given rise to a field of green chemistry, which involves the design of a chemical product and process that minimize environmental problems. One of the principles called atom economy involves, among other things, designing reactions in such a way that the quantity of reactants that ends up in the desired final product is the maximum possible. We can define the percentage economy of a reaction by the formula which we have already studied. Atom economy also must consider substances such as solvents, separating agents and drying agents that are used in the process but are not directly involved in a chemical reaction or are not directly a part of the chemical reaction. Using green chemistry approach, chemists attempt to either reduce the amount or eliminate completely as many of these substances as possible. Those that cannot be eliminated are reused or recycled when possible. Atom economy or atom efficiency describes the conversion efficiency of a chemical process in terms of all atoms involved. In an ideal chemical process, the amount of starting materials or reactants equals the amount of all products generated, and no atom is wasted. Recent developments like high raw material such as petrochemicals caused an increased sensitivity to environmental concerns have made atom-economical approaches more popular. Atom economy is an important concept of green chemistry philosophy, and most of the widely used ways to measure the greenness of a process and synthesis. Atom economy can be improved upon by careful selection of starting material and the catalyst system. Atom economy is just one way to evaluate a chemical process. Other criteria can include energy consumption, pollutant released, and price. Poor atom economy is common in fine chemicals or pharmaceutical synthesis, and especially in research, where the aim to readily and reliably produce a wide variety of complex compounds leads to the use of versatile and dependable but poor atom economical reactions. Now we are going to justify the efficiency of a reaction on the basis of the atom economy, and we are going to create a difference between the classical concept of the efficiency of a reaction, that is the percentage yield, and the implementation and the importance of the latest concept of atom economy, which describes the efficiency of a chemical reaction. So, as indicated previously, most chemists have traditionally measured the efficiency of a reaction by the percentage yield. However, this only tells
a specific part of this story, not a whole story. If one considers the reaction where a total of 4.13 gram of the reactants, that is the 0.8 gram of 1 butanol, 1.33 gram of sodium bromide and 2.0 gram of sulfuric acid. So these are three reactants and the total weight of these reactants is 4.13 gram, and they are used, and at the best this reaction only yield 1.48 gram of the desired product. The question might be asked, what happened to the bulk? That is the we have used total amount of the reactant, that is the 4.13, and only 1.48 gram of the desired product is formed, while the rest of the 2.78 gram of the reactant, where it has gone? The answer is they end up in the side product, that is the remaining 2.7 gram of the reactants are incorporated into the side products or byproducts, which are sodium bisulfate and water, that may be unwanted or unused or toxic or not recycled or reused. Side products are oftentimes treated as waste and must be disposed of or otherwise treated. At best only 36%, that is the 1.48 gram over 4.13 gram into 100 of the mass of the reactants end up in the desired product. If the actual yield is 81%, then only 29%, that is the 0.81 into 0.36 into 100 of the mass of the reactant actually ends up in the desired product. You may calculate this at your own. In the reaction just before you, we are going to produce bromobutane, which is our desired product, and in the reaction is designated by number 4. In the synthesis of bromobutane, we are going to use butanol, sodium bromide and sulfuric acid as a reactant, and they are designated as 1, 2, 3 respectively. So in this reaction, bromobutane is our desired product, and now we are going to determine the efficiency of this reaction, or in other words, we are going to determine the percentage atom economy of this reaction. As according to the formula of percentage atom economy, we need the molar mass of the desired product and we need the masses of all the products in the equation. By substituting these values in the formula of percentage atom economy, we have calculated the atom economy of this reaction, that is equal to 50%. So it means that the reaction is giving us a 50% of our desired product and its efficiency is 50%, or in other ways we can say that half of the reactants are incorporated into the product and half of the reactant incorporated into the byproducts, which are useless or waste for us. So thus, at the best, if the reaction produces 100% yield, then only the half of the mass of the reactant would be incorporated into the desired product, while the rest would be wasted in the unwanted side product. Now we are going to study the efficiency of another group of reactions, or we are going to study the atom economy of elimination reactions. In the elimination reaction, which is just in front of you, we are going to use alkyl halide, which is designated by number 7 in the equation. This alkyl halide undergoes dehydrohalogenation, which means the removal of hydrogen halide or HX or HBr from the alkyl halide molecule. So this is a elimination reaction in which we are going to eliminate HX from the alkyl halide, and this is a common method for producing alkenes from alkyl halide via elimination. So it means that alkene is our desired product in this reaction, and we are going to produce alkene through elimination reaction. The formation of methylpropene or alkene is accomplished by the reaction of 2-bromo-2-methylpropane, which is number 7, with sodium methyl oxide, which is at number 8. In this reaction, atoms of the reactants that are incorporated into the desired product designated by 9, which is our alkene. After the entire discussion of the elimination reaction, now we are going to calculate the efficiency of the described reaction, or in other words, we can say that we are going to calculate the percentage atom economy of the described reaction by applying the formula of percentage atom economy. By substituting the values in the percentage atom economy, that is the mass of the desired product from the balanced chemical equation, our desired product is alkene, so substitute the value of molar mass of alkene, which is 56. The second one is the total mass of the product formed in the balanced chemical equation, so the total mass of the product formed is equal to 205, and this product is multiplied by 100, we will get the value of 27. So it means the percentage atom economy of this elimination reaction is 27. The calculation of the percentage atom economy gives us a poor status of the reaction with 27%. The poor atom economy is a result not only the loss of HBr but also because of the byproducts formed during this reaction. Now here is the analysis of atom economy of addition reactions. Because addition reactions in general lead to incorporation of all the atoms of the reactants into the final desired products, addition reactions result in high atomic economy. From an atom economy point of view, addition reactions are thus environmentally preferable to elimination and substitution reactions. This is the example of addition reaction. If you look keenly at this reaction, this is the reverse of previously described elimination reaction, in which we use 2-bromo-2-methylpropane as a substrate, which is designated by number 7 in this reaction and indicated as a product. On the other hand, methylpropane, which is the product in the elimination reaction, is used as a reactant in this reaction and is designated by number 9. So finally, in this addition reaction, we are going to add HBr in the alkene, or we are going to proceed hydrohalogenation of alkene. As a result of this reaction, alkyl halide is produced, which is at number 7. Now let's consider the addition of HBr to the methylpropane. In this example, all the atoms of the reactants, which is at the number 9 and 11, are shown to utilized in the final desired product, which is designated by 7. The calculation of 100% atom economy further emphasized the excellent atom economy of this reaction. 100%
atom economy of this reaction is calculated on the basis of the substitution of the mass of the desired product from the balanced chemical equation and the mass of all the products in the balanced chemical equation, and this product is multiplied by 100. So by substituting this value in the percent atom economy, the outcome of the efficiency of the reaction is 100%. So we can say that the atom economy of this reaction is 100%. Now here is the description and determination of reaction efficiency or atom economy of rearrangement reactions. Rearrangement reactions involve reorganization of the atoms of a molecule. Because elimination, addition or substitution of atoms is taking place in the molecule undergoing rearrangement, the atom economy of the rearrangement reaction is 100%, and they are environmentally preferable reactions from an atom economy point of view. To illustrate this rearrangement reaction, consider the acid catalyzed rearrangement of 3,3-dimethyl 1-butene, which is designated by 12 in the reaction in front of you, to 2,3-dimethyl 2-butene, which is designated by number 13 in the reaction. In this addition reaction, we are going to describe the efficiency of the reaction or process in a different way by using the different version of the formula of atom economy, which is atom economy is equal to the molecular mass of the desired product, which is 2,3-dimethyl 2-butene and is designated by number 13 in the equation, and its molar mass is 84. So substitute its molar mass. The second requirement is the molecular mass of the reactants, and in this reaction, a reactant is 3,3-dimethyl 1-butene and is designated by number 12 in the chemical equation, and its molar mass is again 84. So this product is multiplied by 100 and we get the 100% atom economy. As we predicted above, for rearrangement reaction, the percentage atom economy of the reaction must be 100%. Virtually all organic reactions fall into the categories of substitution reaction, elimination reaction, addition reaction, or rearrangement reaction. From the perspective of atom economy, addition and rearrangement reaction are highly environmentally favorable reactions, with substitution reaction next. While elimination are the least environmentally preferable reactions. This is the esterification reaction. This is again the type of addition reaction. In this reaction, we are going to react salicylic acid with methanol in the presence of sulfuric acid, and methyl salicylate is the product. In the formation of methyl salicylate, there is the conversion of carboxylic group of salicylic acid into the ester with OH of the methanol. Now let's see the percentage atom economy of this reaction by substituting the value of the molar mass of the desired product, which is methyl salicylate, and its molar mass is 151.2. The second one is the molecular mass of all the reactants, which are salicylic acid and methanol, and collectively their molar mass becomes 170.16.
So this product is multiplied by 100, we get the 89% atom economy. So percentage atom economy shows that this reaction is environmentally safe and is in the benefit of the industry. This is again an example of esterification reaction or addition reaction. In this reaction, salicylic acid reacts with phenol or carbolic acid in the presence of sulfuric acid to form cellol or phenyl salicylate. In the synthesis of cellol or phenyl salicylate, here is the condensation of hydroxyl group of phenol with the carboxylic group of salicylic acid. In this way, antric coating tablets are formed. Now let's see the reaction efficiency or percentage atom economy of this reaction by substituting the values of the molar mass of the desired product, that is the cellol or phenyl salicylate, and its molar mass is the 214.22. The second requirement is the molecular masses of all the reactants. So the collective molecular mass of all the reactant is about 232.23. In this way, by applying the percentage atom economy, we get the atom economy 92.3% for this reaction, which shows that this reaction is highly favorable for the industry and in the benefit of the mankind, and is a friendly proceeding reaction. It is a Pacman reaction for the synthesis of coumarin. Again, it is a type of addition reaction. During this reaction, resorcinol reacts with ethyl acetoacetate in the presence of sulfuric acid to form 7-hydroxy-4-methylcoumarin. In the synthesis of coumarin, here is the condensation of hydroxyl group of resorcinol with double bond COH group of ethyl acetoacetate in the presence of sulfuric acid. As a result of this reaction, an anticoagulant is formed. Now let's see the percentage atom economy of this reaction. By substituting the value of the molar mass of the desired product or the coumarin, which is 176.17, and the second requirement is about the molecular masses of all the reactants, and the collective molecular mass of all the reactants is equal to 240.24. By substituting this value, we get the percentage atom economy, that is the 73.33, which is considerable and comparable with other addition reaction which we have already discussed. Now let's see the current and future impacts of green chemistry. The terms environmental chemistry and green chemistry are two different aspects of environmental pollution studies. The former is the study of chemical pollutants in a natural environment, while the latter is an attempt to design chemical products and processes to reduce the harm they cause to the environment. Green chemistry seeks to reduce pollution at source, whereas environmental chemistry focuses on the study of pollutant chemicals and their effect on nature. On the other hand, environmental chemistry, as taught today, is largely the study of what man has put into the environment and its effects. as well as how to remediate contaminated sites. It is better to prevent waste than to treat or clean up waste after it is formed. It is most appropriate to carry out a synthesis by following a pathway so that formation of a waste is minimum or absent. One type of a waste product, common and often avoidable, is the starting material or reagent that remains unreacted. In universities and colleges, the cost of disposal of a waste from the chemical laboratory can be reduced by carrying out experiment on a much smaller scale. Chemical products should be designed so that at the end of their function, they do not accumulate and persist in the environment, but break down into hazardless substances. It is now possible to place functional group in a molecule that will facilitate its biodegradation. Function groups which are susceptible to hydrolysis, photolysis, or other cleavage have been used to ensure that the products will be biodegradable. Chemical transformations should be designed to utilize raw materials and feedstocks that are renewable. For green synthesis, the feedstock should replace the traditional petroleum sources. For example, benzene used in the commercial synthesis of acetic acid has been replaced to some extent by the renewable and non-toxic glucose, and the reaction is carried out in water. The use of feedstocks that are renewable rather than depleting and less toxic to human health and the environment. The synthesis and manufacture of any chemical substance begins with the selection of a starting material from which the final product will be built. In many cases, the selection of the starting material can be the most significant factor. If the substance itself does not pose any hazard to human health or the environment, for example, but the retrieval and or isolation of the substance causes significant risk to either, then this factor must be taken into account in the selection. Now let's find out the conclusion of the whole story. It is extracted from the story of the atom economy that one should examine each reaction from the point of view not only the yield, percentage yield or yield, but also the atom economy of the reaction. Functional groups of all the starting substances have been converted into another group by synthetic steps by green chemistry reaction, followed by atom economy percentage, which is completely different from the percentage yield. Atom economy and experimental atom economy go beyond the calculations of the yield of a reaction and offer a second way to measure the efficiency of a reaction, taking into account the utilization and unutilization of the atoms of the reactants.
the percentage atom economy and the percentage experimental atom economy give one the means to quantify the atom economy and allows for a quantitative comparison of the atom economy of one reaction or synthesis versus another.